Hello everyone, so I'm going to talk to you about a real-time hybrid simulation technique to simulate the cascading effects of earthquakes followed by tsunamis on bridges. And so a lot of what I'm about to talk about is coming from the simulation paradox. So we have hydrodynamic facilities that are able to simulate tsunami-like wave loading. But the issue is the scale of those facilities. So we could test structural elements, and then we get to the system level, let's say a house, we're really dealing with something that's smaller scale. And then we get to the regional models, we're dealing with something that's quite idealized. And so that sort of gives a rise to this simulation paradox. So you can simulate full-scale structural response under wave loading with computational models, but we might not necessarily have the physical data to validate and support those models because our experiments might not necessarily represent full-scale structural response due to the size and capacity of these existing facilities. And so often what we see is that because we're down at small scale, the structural properties of the system are neglected. So here we have a wave impacting a structure that's assumed to be, let's say, a rigid boundary condition. In the past, there's been some work to introduce a mechanical spring to sort of emulate some sort of elastic stiffness on the structural side, and we can build upon that idea by replacing that spring with an actuator. So now we can supply some sort of harmonic conditions on the bridge structure. But hybrid simulation is really this idea of what if we can really expand what we're testing in these facilities. And so the concept is you have a physical component that's modeled in, let's say, a wave flume here at Oregon State University, and then you're going to couple that to a numerical model of the remaining system, in this case a bridge. And so combined, we can really do something much more sophisticated. So we can actually look at full-scale bridge response, even though a portion of this bridge, this wave structure interaction portion, is simulated physically. And so that's the kind of idea of hybrid simulation. And so for this project, what we did is we physically modeled a bridge pier, and then we numerically couple it to the remaining model, a model of the remaining bridge. And we're just going to show a video here. And so the issue is that because this wave flows in real time, this communication and coupling between the numerical part and the experimental part also has to occur in real time. And so we have an actuator that's taking the displacements and applying them in the physical model, and then we're reading the force feedback, and then applying those in the numerical model. And so that sort of coupling, that communication exchange has to occur in real time. And the nice part about this is that now we can have the that numerical portion of the system at full scale. So we're mitigating this small scale requirement, and then any sort of transfer of information between them, we can scale up or scale down by whatever similitude law we choose. And so we conducted this experiment at our large wave flume at Oregon State University. And we did a number of conditions. So one was a hold condition. And so we just had an actuator at the top of this physical pier, and we held it in place, and we impacted with the wave. So that was our baseline. We then let the actuator move the pier back and forth in a sinusoidal type display shape, and then impacted that pier with the wave loading. And so we could get some sort of dynamic response to the system and look at sort of this moving body and how that affects the wave loading and hydrodynamic forces. And then finally, we did this, what we've been calling hydrodynamic real-time hybrid simulation, which is a combination of this physical pier and then a remaining numerical model of the remaining bridge. And so you can see here, like we have a physical wave impacting the physical component, and then we're exchanging forces with the numerical experiment. Because we could only model one pier in the wave flume, we then copied that wave to simulate the forces on both piers, assuming that it's much more likely that you're going to get wave loading on both piers. And then we looked at a number of different effects. So in an offline way in the numerical model, we could apply some seismic loading and get some damage built into the system before we impact it with the wave loading. And finally, because we could play around with really any aspect of the numerical model, we could look at those hydrodynamic forces, and we could say, oh, well, the wave loading actually has a much higher density because it has sediment in it. And it's picking up all this debris along the way, and so we can sort of play around with the impact of that wave loading in a way that we would never be able to do in our experiment because we have to use clear water. And so this is the final experimental setup that we did for this project. And you can kind of get this vibe of excitement that's happening. So the wave maker is on the far side of the flume. We have our cylinder here, and then it's actually there's an actuator at the top. And that actuator is the communication we have with the remaining numerical model. And so we get the bridge impact. And so in this case, both this pier and the numerical portion of the remaining bridge are being impacted by this wave loading. And so we have some takeaways. So now we can virtually extend our wave flume to really test larger and more sophisticated structures. This approach was feasible, and while we looked at it for this particular bridge system, now we can start thinking about more complex bridges and other types of structures that we might not be able to fit in our existing flume. Now, because we're simulating the wave physically, we actually avoid a lot of the computational costs associated with fluid dynamics or computational fluid dynamics. And so we can accumulate a lot more data in less time, and we can use that data to validate future computational models. And finally, this is a method where we can sort of play around with scaling and play around with the types of structures that we can model. And so ultimately, it'll allow us to test more complex systems. Okay, thank you so much for your time.